So this video is about using Riemann sums to find the area under a curve, and then how we can change that into definite integral notation. Just so you know what a Riemann sum is, it just means we're going to take those rectangles and trapezoids that we talked about yesterday, and we're going to add them up to find the total area. That's just, in general, those are called Riemann sums. We used LRAM and MRAM and RRAM and trapezoids yesterday. Really, all of those methods have their problems. They can overestimate or underestimate the area under your curve. But if you use enough rectangles, then it actually doesn't matter which method you use. If a lot of rectangles is good, why wouldn't we use infinitely many? And if we use infinitely many, then we actually get the exact area under the curve, no more worrying about the overhang. The way we're going to deal with infinitely many rectangles is we're going to use limits. So before we get too far, I want to remind you about summation notation. This is going to be the beginning of this video. Summation notation is when you use this sigma, which is a Greek letter. It stands for sum, and a sigma is a big operator. We're going to have a counter variable. The counter is starting at 0, and it ends at 4. So if I'm going to write this out as a sum, I'm going to say, well, my first term would be for n equals 0, and then I'm going to make another term for n equals 1, and I'm going to make another term for n equals 2, and the next term would be for n equals 3, and then my last term would be for n equals 4. So my very first one, if I plug in n equals 0, I'd have 0.25 times e to the 0 divided by 4. So that would actually be e to the 0, which is 1. My next term would be 0.25 times e. Now I'm going to use n equals 1, so that's going to be e to the 1/4. And my next term would be 0.25 times e to the 2/4, or 1/2. My next term would be 0.25 times e to the 3/4, because I'm just replacing the n with a 3. And then my last term would be 0.25 times e to the 4/4, which is 1, so just times e. If I had a calculator, I could add those things up, but the point is this big long string of addition is equivalent to that sigma notation. You should be able to go back and forth between the sigma notation and the big long string of addition. So here's the big long string of addition for a different problem. And let's say we want to start counting at, I'm going to call it k this time. You could really call your counter any variable you want. And let's say I want to call this k equals 0. And this would be k equals 1. Now I have to be counting by integers. My counter variable can only go up by 1. I can't change what I count by. So these have to be going up by 1s. I could change where I start counting. I don't have to start at 0. I could start at 1, but I think it makes the most sense to start here at 0, and we would end when we get to 5. Looks like each of my terms has a 1/2 in it, and each of my terms is something squared. The way I get what's inside of the parentheses is, well, when k is equal to 0, it's just 0.25. When k is equal to 1, it's 0.25 plus 0.5. When k is equal to 2, it's 0.25 plus 1. When k is equal to 3, it's 0.25 plus 1.5. So it looks like what's happening is we're starting at 0.25 every time, and then we're adding a number of 0.5s on. So it's going to be 0.5 times k. You might not have seen that totally quickly, but maybe if I make it in a table, if I make it in a table with k as 0, and when k is 0, I have 0.25. When k is 1, I have 0.75. When k is 2, I have 1.25. What I notice in my table is that this is counting by 0.5s and that it's starting at 0.25. So my y-intercept is 0.25 and my slope is 0.5. That would be another way of thinking about it. But that's summation notation. That is being able to go back and forth between that big sigma and a bunch of sums. What the rest of this video, the next set of this video is going to do is going to talk about how do you relate that to adding up a bunch of rectangles, and eventually how do you relate that sigma notation to adding up infinitely many rectangles. All right, good luck today. Thank you.